Okay, awesome. So welcome everyone to this Quantum Startup panel hosted by DuQIS and presented to you by Duke Quantum Center as well. First of all, I would like to introduce our organization, DuQIS, Duke Undergraduate Quantum Information Society. We do host a lot of events like this. We host hackathons, talks, and panels like this. We're going to have a graduate panel soon. So if you want to join DuQIS leadership, or you want to help us plan one of these events, or if you just want to subscribe to our mailing list, Nora, here the DuQIS assistant, is sending the link to the chat so you can subscribe to our mailing list and look over our website. And a little bit about myself. My name is Catherine. I'm a senior studying physics at Duke. I've been interested in quantum computing since freshman year, and I've been working with Professor Ken Brown at Duke for a long time. So we're very, very honored to have 5 panelists joining us from 5 different companies all over the world. Unfortunately, one of our panelists from Xanadu won't be able to join us today due to some personal issues. But before we get started, I just want to go over the rules a little bit about the panel. So for the audience, as you can probably see, there's no option of chatting for you, but there's the option of Q&A. So all the questions that you submit to the Q&A will be filtered and selected by some of our students working behind DuQIS assistant. And then those questions will be sent to me, where I will then ask the questions to the panelists. And roughly the breakdown of the panel will be, we'll first start with some basic questions and personal questions, and then we'll go into talking about the technology, and then the business, and then finally the career side of things. And then for the last 5 minutes, we'll just open the floor up to everyone for any last minute questions from any of these 3 topics. So that's basically the breakdown of the panel. And next, I think we should have all the panelists introduce themselves. So tell us a little bit about yourselves, what your company does, when you joined the company, and what role you have at the company. So anyone can start.
Well, I can pick it up if you want. I just beat you to it, Peter.
Yeah, you did.
So yeah, really great to be here. I'm Naomi Nickerson, so I'm from PsiQuantum. So I guess a bit of background on the company. It's a quantum computing company based in Palo Alto, over on the West Coast. And we're building a fault-tolerant photonic quantum computer that's based on dual-rail photonic qubits. So the team at PsiQuantum is very diverse. It's really doing everything from the manufacturing layer, which is a key part of the sort of foundation of the technology, and then everything throughout the stack all the way up to quantum applications. So that covers, things like software, electronics, the packaging, the systems, the control, and quantum architecture and quantum information. So my background was in theoretical physics. So I studied quantum error correction during my PhD. And I've been at PsiQuantum, I guess, for almost 5 years. So I started out when it was really small. I think I was number 5 officially on the books. So it's obviously been quite a journey since then. And I now lead the quantum architecture team. So that covers the design and architecture through to quantum applications. So yeah, great to be here.
Awesome. I guess I'll just call on people to make things easier. I guess, Peter, you were really eager to go.
Sure. Hey, everyone. I am Peter Johnson. I come from Zapata Computing. So a bit about myself first. I am also a theoretical physicist. I did my PhD in quantum computing at Dartmouth College, and then moved to the Harvard chemistry department, and was doing postdoc work in a group that was some focused on quantum chemistry, some focused on near-term quantum computing. And myself and 4 others from the group spun out Zapata to develop software to help use quantum computers and to help companies understand how quantum computing could impact their business. And I guess 3 or 4 years later, I lead our quantum research team. And, you know, maybe you see some papers coming out from us. And we also give support to some of the customer projects that we do internally. So yeah, really looking forward to this panel and learning from everyone here.
Thank you, Peter. I guess, Leo, you want to go?
Sure. So thanks, Catherine. It's great to be here back at Duke, even if virtually. So I have a very long name, but everybody can call me just Leo. Some background about myself. I did a PhD in physics back in Brazil some time ago. After that, I spent some time doing a postdoc at Duke with Ken Brown, that Catherine already mentioned. And after that, I joined Q-Control, and so now I'm here in Australia. So maybe some background about Q-Control. Q-Control is like a quantum technology startup. We work with quantum computing, but not just with quantum computing. We also have an interest in other quantum technology aspects, such as quantum sensing. And we mostly work with, as the name says, quantum control, or like how to develop. We work developing software that will help quantum devices to exert better control of their systems, and thus like extract the most of your quantum computer, your quantum gates, or your other quantum devices. And yeah, as I already mentioned, the main office is here in Australia. We have also an office in the US, and yeah, and we've been around for 4 years now. So I think this is like mostly what I have to say about an overview of myself, the company, and like also looking forward to learning more from the other panelists.
Awesome, thank you. Mark, do you want to go?
Sure. So thank you, Catherine. It's great to be here. So I was actually an undergrad at Duke, and unfortunately, DuQIS didn't exist back then. That was a long time ago. But I did study physics and math, and then I did my PhD in string theory, which actually was a result of my undergraduate work with Ronan Plesser there at Duke. I joined Cambridge Quantum in 2017. I was the first US employee. And so despite my background in physics, I'm actually on the business side of things. So at Cambridge Quantum, we develop software for near-term quantum applications, and we're in the process of merging with Honeywell's quantum group.
Okay, Nam?
All right. Yeah, I just go by Nam. It's because it's easier for me to understand. Yeah. So a bit about myself. I'm a physicist by training, a computer scientist by postdoc. I was hired at IonQ as a systems engineer by first task. I'm the current quantum theory lead at IonQ and also an adjunct assistant professor of physics at the University of Maryland. So about IonQ, it's a full stack company that focuses on trapped ion quantum computing. This is the first pure play quantum software and hardware company to go public. It went public and listed in New York Stock Exchange last Friday on October 1st. So if you search some CNBC video clips, you might see me in the background. And I joined the company about 5 years ago as the single digit employee like Naomi. I'm the first theory and software hire at IonQ. So with that, yeah, turn the mic back to you, Catherine.
Okay, awesome. So I think we're gonna start off with the first question about a little bit about personal choice. So all of you guys are obviously in the quantum industry, and what is sort of the push that made you choose industry over academia, and why specifically a quantum startup versus big tech companies like Google or IBM? Or yeah, I guess why don't you start, Naomi?
Yeah, sure. I can say a bit about my journey to get here. And I think, as is often the case, it's all sort of just about the chances that come up. So I feel like it's a bit of a fluke in some sense, but I feel like very fortunate to have ended up here because I think it's a pretty good fit for me. So at the end of my PhD, I was kind of really in two minds about what I wanted to do, whether I wanted to stay in academia. So I really loved the physics and the things I've been studying. But during my PhD, I'd spent a bit of time working as a software engineer, as an intern at a company over here in the Bay Area. And it was nothing to do with quantum, but I was sort of deciding between these two things. And I went back and forth on it for ages. So I really loved the physics, but I really loved this thing of being part of a team and focusing on something real and being kind of much more integrated with the people that you're working with every day. And so in the end, I chose, well, I'll go and be a software engineer for a while. And then depending on what I feel after that, I'll either decide to go back to academia or to continue. So I did that. And during that time, I mean, it was a fantastic experience. I think it's very eye-opening to work on something different and be part of an environment like that. But I did really, really miss physics. I learned definitively that I love physics and I wanted to spend my time thinking about it. And so then at that time, that's when Jeremy and the others moved over to start PsyQuantum, and I got talking with them, and it was just the perfect combination of these two things. So it's the application of the physics and the chance to do the science that I really cared about, but in this very different environment with a focus on something which is very concrete and in a very collaborative environment. So so that was, I think, how I ended up there. And I think if it's like people have very many different motivations, and I think if you're the type of person who loves that collaborative environment, then it's a really great time for being able to do quantum computing in that world. It's a pretty unique point in the trajectory of quantum computing today.
That's awesome. I mean, quantum is a really interdisciplinary field, and that's what draws a lot of talents and from various different fields to that. And I was wondering if anyone else wants to share a little bit about why, like more on the portion about why small startup versus big companies.
Actually, Catherine, can I give just a quick little anecdote?
Yes.
And I'm thinking of this because, like Naomi, I was also encouraged to go into startups from PsyQuantum founders. So I think it was a conversation that I had with Terry Rudolph at a time when I was trying to decide between continuing in academia or moving to help start Zapata. I had a call with Terry, who had recently joined PsyQuantum, and I wanted to get his input because this was somebody I admired in the field, and I was very surprised that he had joined a startup. And he said that what he enjoyed most about PsyQuantum was that there was this like small group of people that were all focused on the same goal, and that was something he didn't really find in academia. And yeah, I actually think that played a big role in me choosing to join a startup, and that's been absolutely true.
That's awesome. I think if you guys don't mind, we have to move on to the technology sections due to the time given. But I think one of the most interesting thing that people are wondering about is what technology. So there's so many technology platforms that are currently in the race to build the first real practical quantum computers. Just to name off a few: superconducting, trapped ion, photonics, and etc. So what technology, out of your personal belief, will be the most promising candidate for winning the quantum race? And if you could give a little elevator pitch, what would it be? How about Nam? You want to go?
Sure. I'll give an elevator pitch here. In all honesty, I don't know. Yeah, that's the real bottom line. I mean, I like trapped ions. just because they have perfect qubit replicability, clean input and initialization and readouts, have very high fidelity quantum gates, and also they preserve full connectivity within the chain of ions, and also actually full connectivity between the chains of ions. So when I'm writing quantum programs, all of these come together and then make my life very easy as a person who's using a quantum computer, as opposed to, let's say, building a quantum computer. And one of the things I've also looked at is some of the people always kind of complain that trapped ions are slow. I would go insofar as to say this is not true. I'm actually working on many of these theoretical studies where it will actually enable picosecond quantum gates on a trapped ions. And that's natural in the sense that it's based on atom and light interactions. So their time scale is in femtoseconds, so picosecond gates only make sense to me. So that's my 2 cents.
Okay, does anyone want to give a different pitch for a different technology platform? Maybe hear from Leo, because you haven't really spoken.
Well, at Q-Control, like we work with different platforms, so I won't pick one over the others. Like we are happy to work with like trying to improve the control of helping like any kind of client with any kind of platform to try to extract the most, to make the most of their quantum computer. I think like I agree that trapped ions are like very promising. Like superconducting computers are currently like the most used platform, so they currently have like some kind of advantage in the sense of like being most having the most widespread use in terms of like IBM and Google using, but that doesn't mean that it will be the winners in the end. It doesn't mean that there will be like a single winner in the end. Maybe there will be like multiple viable platforms in the end. So yeah, I think yeah, it might be a bit early to try to say which platform it would be, but we are happy to work with all of them.
Maybe I can add,
Yes.
add a comment on photonics. So the PsiQuantum is working on is an entirely photonic architecture, and you know I'm a fault tolerance person by background, and that's obviously something which applies everywhere. And maybe I can just speak to my own motivations for focusing on photonics. And I think there's sort of 2 things that are at the core of that, of the approach that we're taking. And the first is manufacturability. So having a technology where the components that you need to build it are things that can be put into a process that you can manufacture using existing tools or with small modifications. And I think the motivation for that is to get to useful quantum computing. That's going to require millions of qubits, and that requires many millions of physical components. So even for one, small quantum computation that's fault tolerant, you're still looking at a very, very large system with, extreme scaling requirements. Is going to require you to have multiple units that are connected together. And so that manufacturable technology, that's kind of the foundation of our approach. So we're making those components with a tier 1 foundry, with our partner foundry. And so, yeah, I think that's a huge factor in looking for what is viable to scale, is can you connect chips up together, which photons enable you to do in a kind of very straightforward way. They're already flying around, and you can use optical fiber. And then what is the underlying technology? Is it actually capable of scaling? And are you going to be able to provide the system that sits around it?
Yeah, that's awesome. I mean, I've always wondered how photonics quantum computers actually work, because my experience is more with trapped ions since I'm working at Duke. But I guess one of the common themes that I picked up from this conversation is that everyone is trying to strive for better fidelity, always scalability, and in terms of the technology that at this current stage. And we understand that quantum computers are currently very noisy, and there are very few applications that we can find for the noisy quantum computers. So I guess the next question would be, for the hardware or control companies, in this call. What are some of the near-term goals you guys have to improve on the hardware? And for the software companies, what are some of the near-term applications that the company's hoping to achieve with NISQ quantum computers or near-term quantum computers? Yes.
Can I jump in first? So at Cambridge Quantum, we've been a software company for 7 years, and we've very purposely remained hardware agnostic. And so we've developed ways of getting the most performance from any type of quantum hardware. And this is why we developed Ticket, our software development kit, which is language agnostic. So you can use Qiskit, Cirq, Q#, whatever, and execute it on whichever platform you like, IBM, Google, Rigetti, IonQ, etc. And just last week, we announced that it's open source. And so anyone can do anything. Anyone can write their own optimization algorithms, and any hardware group can write their own extensions. And so this is specifically for NISQ to try to get the most performance from near-term quantum computers.
That's all. That's awesome. I guess Peter's having a little bit of connectivity issues.
Yeah, I'm not sure. All right. It might be okay now, but can you hear me all right?
Yes, yes.
Okay. Yeah, well, maybe I'll go ahead and answer. So applications that I'm personally most excited about are in using quantum computers to help solve problems for quantum chemistry, quantum materials, and I think there are some pretty exciting ideas for using quantum computers in machine learning. And yeah, I think some of the near-term goals are to work with a lot of these hardware companies to figure out, like, okay, what resources will it really take to, say, like, achieve quantum advantage for any of these problems. So I'm very excited about that integration between algorithm design and hardware and quantum error correction.
So I guess Zapata is also sort of taking the hardware agnostic approach as Cambridge Quantum.
Yeah.
Yeah, because I was thinking that some of the actual, like, really near-term applications are all some sort of hardware tailored or take advantage of specific hardware structures. But I guess maybe like in some of the full stack companies here or Q Control, what are some of the I don't know, what are some of the progress that you guys are hoping to make in terms of improving the hardware so that brings us closer to practical quantum computing?
So I won't talk about like future promises because I think it varies a lot between platforms and devices. So there are like some kinds of quantum computers that to improve the quantum computer, like we know all the terms of the equations that are describing the quantum computers. In some cases, there is not complete knowledge of what's going on in some parts of what we are trying to improve is actually like a black box that we have to use like machine learning or something to try to extract the most. I think like some past numbers that I can maybe mention is like we had like a paper this year, like improving the over the IBM default pulses for single qubits in their cloud computers about 10 times the infidelity, and I think about 2 times for the cross-resonance gate, which is for 2 qubits. And I think for like quantum sensing as well, like we have like about 10 times of improvement in the contours of some fringes in certain setups for quantum sensing. So this is like more or less the order of magnitude of things that we have published. And yeah, I think I should probably talk about things that we have before I talk about things that are not that I am probably not allowed to announce before. So yeah, these are like sorry for like talking about past results, not future things, but it will depend on the exact platform to see what can be extracted in the future.
And Nam, do you want to share a little bit about IonQ's plan? in terms of hardware?
Sure. Where should I start? Well, we can start with a paper that was published hot off the press today at MPJQI about a optimal control pulse design for ion traps 2-qubit gates. Yeah. So basically, the way the ion trap works for quantum computing is that you load a chain of ions, you kick the ions using laser beams, and at the end of the pulses that you shoot to the laser beams, ions sort of do its thing, and then it implements the unitary that you want to implement, which we typically call as quantum gates. So clearly, if you just shoot the random laser pulses, it's not going to do what you want. So you have to shape it. And to induce the right quantum gate operation on this device, you can do it in infinitely many different ways, just like you can write identity in infinitely many different ways. So the question is, what is the optimal pulse that's going to implement the gate in the most power efficient way, which we know to be the problem in conventional computing, and it's going to be a problem for quantum computing as well, and also induce the quantum gate in a most robust fashion, because no hardware is perfect. So these kind of things are the ones that we focus on at IonQ, at least on the theory and hardware folks, in order to deliver a high fidelity quantum gates throughout the operation time that is to be used by the users of our quantum computers. And what we also do is a bit of an engineering effort. So this is no longer an academic lab, an experiment. So it's an engineering project. So the thing that we learn in engineering 101 is power performance area trade-off. So we readily admit that the models that we have is imperfect. We readily admit that the hardware is imperfect. And so why don't you introduce, for instance, some ignorable amount of imperfection to your design in the first place for your pulses, so that you can enlarge the design space in the first place to then gain in the power efficiency and or gain in the gate speed. Okay, so these are the things that we also study at IonQ and implement and test. And this was recently been highlighted by Physics World. So we have a concrete plan going forward to improve and iterate upon these kind of progresses. So please stay tuned.
Awesome. And Naomi, do you want to share?
Yeah, I mean, I'm maybe not going to answer the question that you asked in the beginning, but I can just say something about our approach, because we're really totally focused on the fault tolerant regime. So we're not looking at doing NISQ applications, and all the work that's done either in the hardware through all the way through to the applications that we're looking at, it's already focused on those larger scale devices. I mean, and what that looks like in terms of our focus on the hardware side, it's really about integration. So all of the components that you need, they exist, they've been demonstrated in different forms, but to actually turn that into a scalable technology, you need all of those components to exist in the same manufacturable platform. So in a single process where you can make a single design, send it to the fab and get everything back. And so that is really at the center of the hardware progress. So earlier this year, there's a talk that Jeremy gave at APS. There's a video if people want to go and watch it, talking about a kind of big step of that, which is getting the detector, the single photon detector, integrated into the chip. So that's sources and detectors that are in this fully integrated system. And yeah, so that's kind of an example of the type of milestones that we're focused on. It's not about kind of small quantum simulations. It's more about these integration milestones that are about developing a system.
I see. Awesome. I think that kind of ties into a little bit, because you sort of PsiQuantum is looking into the future with like actually fault tolerant architecture. So that sort of ties a little bit to my next question, which is, what do you envision the quantum industry to look like in 5 to 10 years? And what will our quantum computers look like in 5 to 10 years? And what roles do you think these startups will actually play in the quantum industry in the future? Peter, do you want to go first?
Sure. Something that I would be really excited to see maybe in the next 5 to 10 years is some abstractions forming that let quantum programmers be more creative with how they use quantum computers. Like I'm thinking about, we're using classical computers with, without thinking about like message passing protocols or anything. So it would be nice to eventually like use quantum computers and not think about like what a Hadamard test is. So yeah, I'm excited for that like future, more abstracted mode of using quantum computers.
Mm-hmm. And Mark, do you want to also comment on that? I
think there will be commercial applications. Right now, we're kind of almost at the verge of that, but I think in 5 years and certainly in 10 years, it will be ubiquitous. People will be using quantum computers and they won't even realize it. They'll go on Google Maps and they'll look for how to get from A to B, and they'll be using a quantum computer. So I look forward to the day when kind of the whole world is using quantum computing without even realizing it.
Awesome. So I think we're a little bit over time for the technology section. There are just a few specific questions in the chat that people have for specific panelists. And I think the first one to Naomi is, do you see fiber optics taking over from RF cabling?
Well, I can comment on the photonic approach. So there is no RF cabling in photonic architectures. So there's a question that every technology needs to answer, which is how do you connect up qubits that are on different devices? Because there's no way people are going to scale up indefinitely on a single chip. And so there are different approaches to that, and maybe some other people here have other comments on other technologies. But with photons, it's really an easy thing to do because you take a photon and you just put it into an optical fiber. So there's no transduction. You don't need to convert your quantum information from one kind to another kind. You're just coupling it into a optical fiber. And yeah, it's really a great thing to have because those things are just incredibly low loss. So it's actually, well, this is pretty mind-blowing to me that you put a single photon into an optical fiber that's 1 kilometer long, and it's got more than a 95% chance of coming out totally fine at the other end, which is, yeah, pretty amazing.
That's really cool. I didn't know that. And I think the second brief question I think it's to Nam. What is the current progress of the 32 ion chain at IonQ?
So if you're asking about the ion chain, this is an easy question. Yeah, already, I think it was 3 or 4 years ago at Q2B, we have shown the capability of trapping 160 plus ions, no problem, which we can actually go ahead and use our controllers to flop each and every single qubit's population. So the real question to answer is the controllability of the multiple qubits that you have in the system. And this is currently under active test, and it is to be announced, I would say, soon.
Okay, awesome. So I think now we're going to start our second topic, which is business. So obviously this is the quantum industry panel, and we're interested in making quantum, getting quantum out of the academic lab and into an actual business, into the real world. So the first question would be, can you guys share any of the founding stories of your company and why was it founded? If you have any if you were like early employees or one of the founders, could you share some of that stories with me or with us?
This was a little before I joined, but in 2014, Stephen Hawking advised our founder, Ilyas Khan. He said he thought quantum computing was going to take off and suggested that he get into this business. And so that's why we're called Cambridge Quantum Computing. Our first scientists were from Cambridge, England.
Awesome. I guess, Peter, you're one of the co-founders of Zapata Computing. So do you have any stories?
Yeah, I guess a brief story is, I think the first moment that somebody was thinking to start a company was actually a postdoc in our group was having a like conversation with our postdoc boss, Alon, about like what career direction to take, you know, considering like academia, national labs, joining a big company in industry. And I think Alon was like, or we could start a quantum computing startup. And I think this postdoc, Johnny, was like, yes, that's what I want to do. And so then Johnny asked me, hey, do you want to join this startup? And I said, no. And yeah, I think it was, I don't know, over the next few months, talking with different people, talking with Terry Rudolph at PsiQuantum, that I realized this would be a great way to keep working with people that I really liked. So I guess Zapata came out of a career conversation. So maybe the takeaway is have those conversations with your mentors.
Awesome. Leo, do you want to share a little bit about Q Control and how they started?
Yeah, so actually, like I joined Q Control like 2 years after they started, so I don't know the founding stories. I wasn't one of the founders, but yeah. So I'll let the other panelists who were earlier members of their companies to share their stories then.
Okay. Maybe Nam, you want to go? Oh, sorry, Naomi.
Oh, well, yeah, I mean, this isn't so much a story about the beginning, but maybe just talking about the motivation for why to take something from the university and turn it into a company. And I think the motivations of you know, Jeremy, Terry, Mark, and Pete when they started PsiQuantum was, I mean, it was really founded off a desire to actually build a technology and recognizing that, you know, they've been doing this in academia for, I don't know, 15 years or something beforehand. And it gets to a point where the progress that you need to make to take something, to turn it into something real is not the kind that you're incentivized to do in any way in academia. So it requires, you know, a whole collection of different expertise. It requires the kind of work that's about improving something by 2x, the kind of thing that there's, you know, no incentive to really push forward within that academic setting. And so I think, you know, for them, that's really the motivation to get started. And now I totally see that it's kind of work that, you know, you just have to have this much more collaborative and environment with many, many different kinds of people, most of whom are actually not quantum computing people by background at all. It's people who have actually built things before, you know, used their hands and built products and delivered things.
Awesome. Nam?
I'm outclassed here because both of our founders of the company are already there at Duke University. I'll just say something, and then if I get it wrong, they can clarify on their own, I suppose. So the company was founded in 2015 by Chris Monroe and Yunseong Kim. So to the best of my knowledge, basically there was this guy, Harry Weller, who has since passed away in 2015 from NEA, who read this PRA paper that they have published, the two founders have published, and then walked to Chris's office and knocked on the door and asked whether they were interested in starting a startup company. And that PRA paper basically read like a business plan, according to Harry himself. So this is how the company has started, but it hasn't really taken off since until 2017. Since then, we've raised like $84 million from VC and $600+ million for going public. Yeah, so Chris is actually the world's first to realize a 2-qubit gate on any of the platforms with Dave Vineland. Yunseong Kim's PhD advisor, Yoshida Yamamoto, is actually the first to propose a quantum gate in the world. So the two founders have a very long history of dabbling in quantum information for nearly 2+ decades. Most recently, as you know, probably, Catherine, we have also published a logical qubit realized on a quantum computer. And this is going to be the stepping stone towards realizing a a error-corrected qubit on a trapped ion device going forward at IonQ.
Awesome. All of that sounds like great advances in the field. And I think the next question to ask is, so obviously business needs money to fly, and a lot of the work that are currently being done at all of your company, all of these companies are still pretty much a lot of research and development work. And I was wondering, so if you guys know behind the scenes, so what were the investors most skeptical about quantum computing at first? And there's also a lot of conversation around the hype that we're generating in this field, in the industry, in the quantum computing industry, that might be good or might be bad. So what are some of your guys' thoughts on investments and also hype in the field? I guess, Mark, do you want to comment on this since you're the business?
Sure.
You're working on the business side of things.
So I'm usually the first point of contact when a company's interested in working with us. I usually speak with them, and I'd say 99% of the people I speak with have a misconception about quantum computing, and it's at the two extreme opposites. About half the people I speak with, they don't believe quantum computing exists, that it's some sort of science fiction buzzword, and it will never happen or something. And the other extreme is they think quantum computing exists and it's super powerful, that it's infinitely powerful, that they just run their existing software on quantum computers, no matter what the program is, and they can be running their business off this next week. And so I kind of have to explain, we do have quantum computers. They can do things that are interesting, but not quite commercially advantageous. We think in a few years that will change. It's for very specific applications, but you should start working on things now because it takes time to develop this and develop your quantum muscle, we call it. And if they'd still like to keep talking after I give that speech, then we connect them with our scientists to discuss specific projects. So that's kind of usually how it is giving them an honest appraisal of where we are and what it can do, because there's a lot of misconceptions out there.
But that's more for clients. But what about like investors?
Investors also, I don't know, one of their friends mentioned quantum, and so they want to invest and get into it. And I have to explain there's going to be a time scale. It's going to be a few years, or they're phobic about this. They're like, oh, I'm not touching that. It'll never exist. And I explain it already does. So it's similar.
I see.
Actually, I have to say, Mark, you've probably talked with way more investors than me, but I have been extremely impressed by VCs and their grasp of where the industry is, and many times it's like they know more about the existing quantum computers than we do. But I think their hesitancy is in not knowing the timelines of how these devices will progress. And I think there are a lot of people who have been informed about quantum computing for decades, and they feel like they've been tricked in the past. But I think something that's different nowadays is that the devices are from most of the people on this call, except me, the devices are progressing really rapidly. So I think that really helps investors get interested.
Yeah, I sort of want to touch a little bit about the second part of the question, which is all the hype. Some people in the academia are very critical of the hype that some of the the industry is creating in order to draw in the money. And sort of what is your guys' take on in terms of the hype that are created in the industry, and what are we able to deliver to that expectations that people have for quantum computing? Nam, do you want to touch?
Sure. What does hype generate? Well, it certainly generates interest and attention, both positive and negative kinds. Yeah. I would say usually I kind of buy into and get the salesman's pitch. Like if you're buying a car, it's like, this is the best car in the world. I get it. Okay. But we really have to live up to what we announce within reasons. I understand if sometimes the roadmap is a little off here and there, but if you're too off and if what you're announcing is completely outrageous, this is not doing anybody good. So we really need to take up on the actions to deliver things that we have announced to the best of our ability as a community together, because otherwise it can be a real net negative overall. So we really have to be cautious over there.
Yeah, I think I agree with now, because I think like personally it's nice that there is like excitement around quantum computing, but I think we like there's like some preoccupation like in the company that we should like try to make the promises realistic, and that like it's good if probably like the industry as a whole keeps their promises grounded in reality, and this will like probably help keep everybody's expectations in like within the realm of the possibilities, instead of just like frustrating everybody with something that's not deliverable. And but yeah, I think like despite that, like it's nice that the industry is currently in a situation where there's like excitement around something new that we are building. It's like it's good to be in this environment. Yeah, and the disadvantage is that there is like clearly there are like bad actors that will use this excitement for their own bad purposes. There is like probably everybody has seen like quantum scams that just like plaster quantum into like something that's just like nothing related to anything even remotely quantum, and that's like just like it's not even quantum, and it's not good for anybody. So yeah, so yeah, so I think it's sort of
Maybe I can follow up on that, and because I think it's a really interesting topic, one that's very present. And I think there's a perspective in which the hype, like there should be a lot of excitement about quantum computing. Like it really is a transformative technology. Like it has this potential, which is so rare, to really provide an exponential speed up over something we can currently do. And I think, you know, that's something that should be communicated and people should really grasp. There's the reason that we're all so excited about it. And that's obviously challenging to do in exactly the right way. And the danger is that because it's intrinsically challenging to communicate like really what quantum computing is, that things turn into something which is giving a wrong message, and that hype is kind of telling a misleading story, or one that is misinterpreted. And I think, I mean, there's a bunch of risks that come from that. And one that I worry about a lot is that it directs resources to the wrong places, to the places where not the real challenges are. So I think an example is like one of the most important things that the whole community needs to care about at the moment is increasing the number of really concrete applications that we can talk about. So, you know, here is a specific molecule that this company wants to simulate for this purpose. And if we have a quantum computer of this size, then we can solve this. And there's kind of this whole field of places where we know those things are going to come, and you can say, you know, abstractly, this is going to be a gain, but it's actually very limited, the number of, you know, fault tolerant applications that have been worked through to that extent. So I think, you know, a danger of hype is that things like, you know, students, maybe like we want people to spend their resources, their time and their brain power on the problems that really matter, or governments to invest money in the places that are going to have the most impact. And so, yeah, hopefully we all like need to play a role in trying to shape that narrative to be the one that's really going to propel the whole field forward in the best possible way.
Yeah, I think that's really, really great in terms of the benefit of the whole field of dealing with hypes. And just something that randomly popped up in my head when Leo was talking about people just slapping quantum on completely quantum unrelated things. Like I have this dishwasher detergent that says quantum and supposedly it's better than normal dishwasher detergents, but you know, the quantum advantage is debatable. I think so. We have a little bit more time. I want to go into the last sections of our panel, which is a little bit about career advice. So of course, the first question would be, what sort of career, what is the best piece of career advice for that you can give to students who want to enter the quantum computing industry? And maybe also specifically for Leo and Mark, how did your guys' time at Duke sort of helped you to get to the career that you have right now?
I'll go first. So when I was at Duke, actually, I should say I started out in engineering. My first year, I was in the engineering school and I hated it and I wasn't good at it. And I didn't especially like the other engineering students. And so that was kind of a miserable first year. It was actually a summer job I had at Caltech JPL that the next summer that really got me back into physics. And so I was very excited about it. And I started working for this professor who was a string theorist, whatever that was. And so that was what led me to get into theoretical physics. It was only much later, as I mentioned previously, that I got into quantum computing.
Leo?
Right. Yeah, I think like my time at Duke has been like instrumental in like being able to enter the industry. I think like as like we already mentioned, like I think Ken Brown's support and advice has been like very important in like helping me shape this career. And I think like getting this experience at Duke, I think like people who work in quantum computing at Duke are very privileged in the sense that they can really have like have contact with so many different aspects of quantum computing and like real devices next to theories and also like different applications of quantum devices all like working together. And I think like having contact with all these different aspects of the quantum environment of like the different actors of that form this field was very important to like get a holistic view of everything that's going on and how I wanted to fit in all of that. So I think like yeah, I think people who are at Duke, they are like at a very good position to play a role at this industry. And I think like having good conversations with your advisor is also important to help shape your career, help guide your future paths.
Awesome. Yeah, that just reminded me of Peter's advice of talking to your mentor. Maybe you will just start a quantum startup company one day. I think, yeah, Naomi, Nam, Peter, do you guys have like a piece of career advice that you would share with the students here?
Actually, just, yeah, I would just reiterate, I guess, what I was saying before, but like talk to people. You know, everyone here is super friendly, like, as you can tell. So yeah, I guess something that I'm realizing more and more is that like the industry of quantum computing is just like a bunch of people, you know, like pretty normal, friendly people. So reach out to people, and if they don't respond to you, it's probably because they're busy. It's them, not you.
Yeah, maybe what I would say is I think something that I only really came to appreciate after you know, working in industry and spending time with people is that there's not one measure of how good someone is at physics. And really what, you know, we're trying to do is have a team where everyone has different skills that fit together and people are really playing to their strengths. And so, of course, part of that is technical, but then there's all these other things that sit around that are enablers. So whether it's like fantastic communication skills or like amazing software engineering or like data analysis, you know, whatever it is, all these skills that go around it, I'd say it's, you know, figure out what is your strength and then play to it, because those are going to be real enablers when you're trying to work in a collaborative environment. And that's certainly one thing that we're always trying to think about is how do we find additive skills for the team, not just as individuals.
Nam, do you want to?
Sure. Catherine, you've worked with me before to know this, but my advice is always that shoot for the galaxy, and then if you miss it and then land on the moon, that's okay. Yeah, that's as good as a moonshot. Yeah. So just go for it. Go for something risky. Go for something big, and if it works out, it's great. If it doesn't work out, you've still learned something. Yeah. So as a student, this is a luxury that you can afford. So please take advantage of that. So be successful. Yeah.
I think, okay, so I think one of the questions from the audience was that everyone here in the panel obviously all have your PhDs. So someone was wondering how important or how essential do you believe a doctorate degree is to work in the industry? I guess, does anyone want to comment on that?
We can say like something. So like not everybody in my team has a PhD. So I think like most of them have, like, so having a PhD helps. But depending on like what you're trying to build, like it's not the only thing that counts. So sometimes like we need a skill that someone acquired working in a different industry. Like if someone learned a lot about machine learning by working on on another company that needed machine learning, that's also a skill that might be needed in the industry. If someone learned a lot about software development also by working instead of having a PhD, that can count in a team. So it's like having a PhD helps, but it's there are other skills that can also fit within the quantum industry.
Awesome.
I can follow up on that and say, yeah, I think it's absolutely not needed to work in quantum computing, and it really depends much more what type of work and what area you want to go into. So a PhD is it's training in research, and so there are many other aspects of quantum computing development that are not about research, that are about engineering or software engineering and development of other kinds. We have, across PsyQuantum, there's a ton of people from different backgrounds, but within quantum architecture, we have 4 people, I think, on the team who joined us as interns, like after either a master's or an undergraduate, and have come on as full-time employees, and they're all fantastic. So yeah, there are different routes to take, and it sort of depends what you want your focus to be.
Okay, awesome. I think we're almost out of time here, and if we can have one more question. I think someone in the audience asked, what is your response to those who say that quantum computers are getting a lot of interest but will fade soon? So maybe more of a related question to that, would you expect something like a quantum winter to happen? I guess someone who hasn't gone for the last question. Mark, what do you think?
I don't think it's going to fade. I think it's now been established pretty well that quantum computers work, and we're making extraordinary progress. I think there was a risk several years ago of there being hype and then a quantum winter and fade. But I think now, the joke I've heard, it's now an engineering problem. It's not a physics problem. We've shown that they work, and so I think that's very unlikely now.
Okay, awesome.
Maybe I'll add something that Naomi
Yeah.
brought up earlier, which is I think that to overcome a quantum winter, it will be very important that we identify like really valuable industry problems. So I think there's a lot of work to do in that direction.
Mm-hmm.
So maybe to the people, I would say, stay tuned for that.
Awesome. I think there are 2 technical questions, but I think we're over time. So maybe can ask it offline, or if you guys are able to share contact information or like the website of your companies in the chat, for people to learn more about what each of the quantum startup companies do and what they work on, that would be great. But otherwise, thank you all for tuning in to today's panel. And I think we had a great discussions about the quantum computing industry and startup companies in general. And thank all of the panelists for joining us today and in all different time zones. And yeah, and thanks for the audience for tuning in today. But yeah, I think that's it for today. Thank you.
Yeah, thanks, Catherine, for hosting us.
Thank you.
Thank you.
Thanks for joining.
Good to see you all.
Bye, everyone.
Bye.